Everybody, it's a real pleasure to be here with you folks. A real treat to be at McMaster. It's like being asked by the big kids to come and play with them. Yes, I'd be happy to. So I wanted to share with you folks today what I've learned about physics teaching from the physics education research community. If there's anything that you'd like to look up, I have this presentation available on my website. So if something goes by and you don't have a chance to jot it down, you can feel free to track it down there. But I just want to take a moment to thank Sarah and my other hosts for today, because it's been a delightful time here at McMaster chatting with all you folks. So I'd like to begin by talking about, well, what do you do with a physics education? Many of you may be in that situation where you're thinking about, okay, I've got this physics degree. Well, you see, back in the olden days, if you did really well at your quadrivium, you could get some pretty decent employment casting fortunes. Hey, you earned a good buck, the working conditions are not too bad, and people would think, oh, you have this magical, mystical ability to divine people's fates from the stars. And it wasn't all just the kooks and the quacks going into this. Some very reputable people applied this trade. But then along came the scientific revolution. And the astrologers and so on were swept out of the academy. And the sobriety of empiricism helped to pull back the veil. And when that happened, we learned something very important, that the abilities of these astrologers were somewhat illusory. So we can't apply this trait very much anymore. It's now the job of C-list Hollywood stars. So what do you do with your physics degree? Well, a lot of us go into teaching. This is a big part of what many of us do. And we've all seen the power of great teachers. A great teacher can dazzle their students. They're hanging on their every word and action. And it can be very inspiring to have a powerful, charismatic teacher. They often have that ability to stand on tables. And it's funny, I like to drop the textbook and the piece of paper by standing on the table in my classroom. And whenever I do that, I can almost see the students thinking this. Whoa, now he's really teaching. He's on a table. And so where does this power of teaching come from? Well, why not consult one of the great physics teachers? So this is Richard Feynman presenting a lecture at Caltech. He did the introductory physics course there for a while. And his classes are legend within the physics community. This picture is interesting for so many reasons. But he is a legend amongst physics teachers. And his lectures are so insightful that they've been compiled and passed down. I don't think too many of our lectures will end up this way. But he came face to face with the limitations of his powers. At the same time, well, I think many of us do. When truth becomes most apparent, when the final exams come in, and we really learn the limitations of our abilities as teachers. With that large lecture course that he was instructing, he was absolutely shocked and dismayed by the raw number of students who did terribly on the final exam. This was a real surprise for him. And in his introduction to the volume, he talks about this. And he says, well, there were 1 or 2 dozen students who got it. So that was good. They were the ones that I was trying to get to, after all. And I think this is a feeling, an experience that we can all sympathize with. But it's something of a fig leaf that we use to cover our pride when we see the real results of our teaching. And an individual as brilliant as Feynman was confronted with this, but didn't move to the next logical step. So when the great teachers are measured against this question here, they often perform extremely well. They're absolutely engaging, riveting, insightful. But if we change this question a little bit and ask, well, how well are the students learning? The measure could be quite different. And this change in mental mindset is a very important one for us to make. So, how do we answer a question like this? Well, let's think about our typical physics student. We do our best to transmit our finest physics wisdom, those hard-earned gems of understanding. And the real question is, how much actually gets in there and stays? How do we answer a question like this? Well, we begin, as all scientists do, by trying to measure. And we develop an empirical test to help quantify, well, what is sticking? This is a sample question from the now famous force concept inventory, which was introduced about 25 years ago to the physics community. And these questions are exemplified by a focus on the core physics concepts. And they have little or no numbers in them at all. So with this question here, I'd like to actually take a moment and think about your response. And please turn to a neighbor and share your ideas. What do you think is the correct answer to this physics question? 30 seconds. Go.
I'm thinking that. I'm feeling it.
I get the sense you're a pretty quick bunch, so we'll cut off the discussion there. So the correct answer? E. It is B. That's right. Now, if you give a question like this to a grizzled veteran physicist, they'll say, "What? These questions are way too easy." But they have proven to be a revolutionary tool for us to have that first glimpse at what is going on inside our students' minds. When we give this battery of 30 multiple choice questions to our physics students in high school or university, we find some very surprising results. If we administer them at the beginning of the course and at the end of the course, we have a way of measuring how much our students have improved. So we can compare their score before. Maybe they scored 30% on the test. Afterwards, maybe they scored 70% on the test. So they improved by 40%. So if we plot the data from traditional physics classes, the results are very surprising. There is a clear cutoff marked by this dashed purple line for the success of lecture-based traditional instruction. All the samples they made, including courses conducted by award-winning, legendary physics teachers, they were all falling in this very low improvement range. And just to help make the comparison, because some students start off at a much higher level, if you normalize the results, so for example at 70, these students could improve by a maximum of 30%. How much did they improve? You can put that into a ratio. We call that the normalized learning gain. And what did we find? 23% for traditional instruction. This was a shocking result for physics teachers at all instructional levels. So what it means in terms of our students is that with all that hard work that we spend transmitting our physics wisdom, only 23% of it sticks. They only improve by 23% of what they could have. What happens to that other 77%? Well, who knows, really? Scattered as heat in Star Trek trivia. So, this was a very sobering result for the physics community. And it's helping us to focus our attention on what it means to track how well students are learning. And we've all had a sense that this was in fact the case, even if we never quite admitted it to ourselves. Because if you've taught, then you've probably had this experience where you're putting together your best lesson ever. You come up with a fantastic idea, oh yeah, this is the key insight. And then you organize it so carefully, and you show them something amazing that boggles their mind. And you're convinced that you've done this, you've taught them so well that even monkeys can do this. Come on. And then along comes the midterm or the final exam, and they bomb it in epic style. And you're left wondering, what the heck is going on upstairs? Why did I get stuck teaching this course? And when do I get to go back to my research? This has happened to all of us. We've had that experience. And now that we have this wave of empiricism coming into education, now that we have scientific tools to approach this problem, we can use the tools of a scientific revolution of education to help change that instinctive reaction to how our students do, and change that into a much more productive scientific question. What is going on in their minds when they learn? And this is really the starting point for us to help change the way that we teach. So let's take a look inside their minds. And the goal of physics education research is to create a model, a theory that helps us understand the process of learning. And we want to use that model to help us develop our courses. And then we try teaching those courses. And then we research the results. And within the physics education community, this is an iterative process where we build, tinker, and refine that model of learning. And this is really exciting for us as physicists because we are experts at modeling. We're legendary for modeling. Many of us have careers established on modeling. Albert was just ripped. So what are some of these models of education, of learning? Well, the most familiar one to us is best exemplified by this image here. I would just unscrew the student head. We pour in the interesting green liquid, which is hopefully really high quality liquid, our best liquid. And then we screw the lid back on. Maybe we haven't been putting it back on tight enough. Was that the problem? But this is one very common way of thinking about learning. But through physics education research, there's another very promising model. And it has a suitably fancy name. Epistemological resource framing. So what does this mean? Well, it tells us that knowledge, the knowledge that we have, the knowledge that our students are in the process of building, is built up from primitive little pieces. Pieces of knowledge that they intuitively extract from just their day-to-day experiences in our three-dimensional physical world. Ideas that, to the average person, are obvious and need no further explaining. Force moves objects. Increased resistance, less result. Stronger influence wins. These are all obvious kinds of things which may or may not correspond to our more sophisticated physics ideas. But these are the ideas that we generate as we grow up from kids. So we have these pieces that begin to form our later understandings. And as we learn, we form connections between these pieces. The connections will become stronger or more numerous according to that learning. And as time goes by, we develop and create a very complicated network of these little knowledge pieces, cognitive resources as they're sometimes called. And this web of connections represents our more sophisticated understanding. So what happens when it comes time to use this knowledge? How do we activate these resources? Well, it turns out to be a surprisingly tricky thing. Depending on the context that you're in, one particular web or path in that network might get activated. In another context, a different web or network gets activated. It's contextual. Another idea is the epistemological frame. Now, this is a fancy way of saying our brains filter out knowledge or sensory input based on a kind of mental point of view. It's kind of a survival mechanism that we've developed to help make sense of the vast sensory input that we have, and also make sense of the vast reservoir of knowledge and information we possess. And so our mental point of view activates certain portions of these networks. Depending on the situation, your epistemological frame might tell you, oh, this is a force situation. And so then you look for force ideas, and you naturally discount anything else. Or maybe it's an energy situation. Or sometimes it's the kind of knowledge that you're looking for. Maybe it depends on your feeling that, okay, I have to look for knowledge from an authority source. Right? We had that lecture this week, and there's only one equation from that lecture that involves entropy, so this has to be the right equation to use. Or maybe our frame is telling us, this is a situation that we need to make sense of. We're in an elevator, traveling upwards and slowing down. How does that feel? Can I connect that with what I know or understand? And depending on the frame that students are in, they will activate or make use of the knowledge in very different ways. And so, depending on time and place, students' understanding can seem very transient. It can be there at one moment and not there at another, because it depends on these various factors. One final piece that we should understand about this model of learning is that our students come into class wired. And that's not just from the tall cups of coffee that they bring in. It's from their life experiences. They already have a lot of learning having taken place. And those connections are quite strong in their brains even before they reach us, whether or not that's high school or university, because of all those personal experiences and any prior schooling that they may have had. So there's a lot of connections in there already. Now, with this model of learning, we can start to explain what we observe in our classes. We can start to test the success of our pedagogical strategies. So let's take a look at some examples which might sound very familiar to you. This one's provided by Eric Mazur, who teaches first-year physics at Harvard University. And in one of his exams, he gave a question, electric circuit question, looked like this. And, you know, the circuit looks a little bit weird and tricky, but they're Harvard students. They're pretty decent. And their score, the average score for the class on this question was about 75%. So, okay, they did fine there. And he put a second question on the same exam. And it looked like this. And he asked, well, what happens in the circuit when we close this switch here? What happens to the current flowing through the battery? What happens to the brightness in the bulb? It's interesting but there's no numbers in this question. I'd like you to take 30 seconds and turn to a neighbor and share your thoughts. What do you think is going to happen when we close this switch? Go. It's okay to do a bit of thinking first.
Circuit's complete. Okay. I should probably know that for next semester.
Yeah, maybe.
It's TA1E. Well, it would skip that one completely. It would skip the one that's far off because you want the path of least resistance. It would just go through the inner loop. Right? No, I don't know.
I'm gonna go.
You'll see a lot of pointing at the screen. All right, folks. So when Missouri gave this question to the students and looked at the results on the exam, they were very surprising. Now, as experts, when we look at a circuit like this, we say, oh, okay, well, that's no problem. When we close this switch, it short circuits that other path. What happens to the overall resistance of the circuit? Right, there's one fewer path for the current to flow through. So it goes down, and the current to the battery. So to the students, this was a real stumbling block. 40% was the score on the test. Now, we teach all these ideas. Missouri taught all these ideas. So how come the kids weren't able to make use of them? Another example comes from the famous Korean cram schools. I'm not sure if you're familiar with these. But after your regular high school class or day, you spend the afternoon or the evening going to cram school, where you do a bajillion problems in the desperate hope of getting into university. Now, these students demonstrate a very high proficiency with mathematics and a lot of success solving traditional math problems. But the researchers gave them a different kind of problem. Let's say you have a ball rolling up and down an incline. Draw the acceleration vectors for the ball at each of these moments in time. And what do the students tend to draw? This. Now, as the experts, we know that those aren't the acceleration vectors. What did they draw? They drew velocity vectors. But, we spend a lot of time in class talking about acceleration and velocity, clearly distinguishing these things. So we're pouring the information into their minds carefully, right? How does it get tangled up like that? Well, our epistemological resource model helps us to understand that those connections are still not properly formed. So you think, okay, to help them make those connections really firm and clear, we're going to show them some awesome demonstrations, right? This is what really gets them. Well, the interesting thing about demonstrations is that students don't see what you and I see when they're presented with a demonstration. In fact, if you compare their ability to either predict the outcome of the situation or explain what's going on, after having seen the demonstration, it's only improving by 15% compared with just talking to them. So very ineffective, these demonstrations. And we can understand this with the epistemological resource frame model. Because when you're in a certain frame, you filter out information according to the things that you're expecting to see. And we do this all the time in our day-to-day lives. We can be presented with the exact same thing, we can see something very different. This is a fundamental part of how our minds work. We filter out the information which is either not interesting or perhaps inconvenient, and we draw the conclusions that we want to draw. It's the same thing when we show students stuff in our physics classes. So, overall, this model has much greater explanatory power than the old just filling up the minds with knowledge model. And so this is the one that physics education researchers are trying to build on and improve. It's not yet an empirical model, but it seems to have a lot of the right ideas to explain what we see happening in our classes. So, now that we have a reasonable model, what's our next step? We want to think about our educational goals. Now, who is this dashing gentleman, you're asking? Well, this is the fellow who helped to bring us such condensates as the Bose-Einstein. And this is Nobel Prize winner Carl Wieman. And as his second act, he has turned his attention to science education as one of the most important problems for us to tackle. And in his opinion, what our goals as teaching should be is to help our students practice the skills and behaviors of experts in our fields. If that's mathematics, engineering, physics, biology, chemistry, you name it. We want to practice these skills. We want our students to practice these skills. So, this is another characteristic that we can measure. And we can ask our students questions, simple questions like this. When I'm solving a physics problem, I try to decide what will be a reasonable answer. This is what experts do. Or I think about the physics I experience every day. And when we measure the response to questions like these at the beginning and end of instruction, the results are even more surprising than the forced concept inventory. We see clear and strong negative shifts in their expert-like attitudes towards learning and doing science. So this is for UBC and the researchers who developed this survey. Our introductory physics experiences are making them less like experts. And this is something that should worry every undergraduate chair who's thinking about retention of students. So let's think about that novice brain. What's happening there? We see, if we can imagine those pieces of knowledge, they're all broken up. They have relatively few connections between them. The knowledge is fragmented. And they have very little context to attach that knowledge to. They don't have the rules and the skills to decide when that knowledge is useful. Compare that with the expert, and they have that rich web of resources. And that knowledge is highly contextual. This is what allows the expert to see through all those surface features and understand, oh yeah, this is a conservation of momentum problem. And our students often fail to do that. So from this point of view, our educational goal is for us as physicists take this, because it means we've been able to translate the problem of education into a genuine physical problem. It's about helping our students rewire their brain to make the physical connections that create that rich web of knowledge resources. And the research is starting to show this happening. As students learn skills, we can give our first glimpses of the growth of, in this case, gray matter in these different regions of the brain. That's what we're seeing here, as they learn. So this is actually happening. The brain is changing in a real physical way. And then if we stop using the brain, or those skills, we see the atrophy, the decay. So with this educational goal, we can change this into an instructional goal. So what should happen in our classes? Well, the long and the short of it is, what's really important is not how you present the material. It's the quality of the learning environment that you create for those students. Does that learning environment provide them with the opportunity to make that rich set of connections that they need to develop a deep understanding of physics? And there's one thing that doesn't promote deep learning, and that's this: traditional instruction. Now, just in case your irony meter is going off, and here I am talking at you guys, right? Traditional instruction is very good at transmitting information, but it is proven to be very inefficient at building deep understanding. And to understand the ideas that I'm sharing with you today will require a lot of time and effort on your part to help make those connections in your own brains. What does help our students build those connections is active learning. So active learning is basically the opposite of direct instruction, where the students are actively engaged in activities or discussions. They're talking to one another. They're sharing their physics ideas. This is active learning. And this is all rooted in what we call the social learning principle. This was a real shocker to physicists. But no great surprise to the rest of the world out there, that human beings learn best through social interactions. But I bet if you think back to your own experiences, you probably felt that you, in fact, learned the most when you had that discussion in the common room as a student, or when you were forced the night before to put together that lecture for tomorrow's class, but when it was your turn to do the explaining. We need to provide these opportunities to our students. In a very large meta-study, researchers showed that courses that use active learning techniques significantly decrease the dropout rate, the failure rate from those classes. And this should warm the hearts of all our undergraduate chairs. And if we measure students' results on either traditional course exams or specially designed concept inventories like the forced concept inventory, then we find significant improvements once again across a wide range of disciplines. And that might have gone by too fast. Take a look there. Physics, all the others. They're leaders of the pack, right? We have the most practice and experience with this of all the disciplines. And look at that. About 3/4 of a standard deviation of improvement in student scores. And these are solid empirical results showing the efficacy of active learning. Now, if we go back to that data that I showed you before for traditional instruction, with a normalized learning gain of 23%, for active learning, they're almost all clearly ahead of that traditional instruction, with the average value of 48%. So in an active learning environment, students are literally learning twice as much as traditional instruction. It's like getting 2 degrees for the price of 1. That's an awesome deal. So, here's a quick glimpse of my own class.
No, it's so probably they give you the coefficient of friction, they give you the
I forget this. It's crossing against almost our piece. If you're crossing against
There's too much. That's what
no, but the block ones are negative.
Now, we don't have time for a quick discussion here, But I'm hoping you are thinking about what's going on, what's happening. This was our grade 12 physics final exam. And we begin our final exam with a group discussion phase where they take a look at the questions with the numbers removed. And they talk about them. And then they switch back to an individual style, and it looks like an old-fashioned exam. So the way that we change our instruction can vary in so many different ways that support active learning. So if we boil this down to how can we improve our instruction, it's all about the quality of that learning environment that we create. And it's really important for us to understand that the knowledge that we possess as experts is simply not in a useful form for our students. If we try to pluck it out and give it to them, they can't make sense of it. And what works best is that active, discussion-based learning process. And especially one where you focus on the concepts first. Then you help the students to build up the ideas, the formalism, and finally the mathematics. This strategy helps our students make the deepest and most robust set of mental connections. Now, in many of your minds, I can hear the yeah buts. And this is really important for us to talk about. But we succeeded. For many of us, we did very well in the traditional educational system. But we have to remind ourselves that we are not the average student. And the things that motivated us to learn, the things that excited us and worked for us, really don't work for the average student out there. So it's very important that as experts, we don't mistake ourselves for our students. And the fact that it worked for us only means that it worked for us. And as experts, we suffer from expert blindness. We've forgotten what it's like to learn, to face these ideas for the first time. Well, there's other reasons that might discourage you, because there's all that content to cover. Well, it's critical to liberate ourselves from content. And there's one technological innovation that our system has yet to fully deal with, and that is the printed book. Because this remarkable invention liberates us from the task of just presenting information. We need to have our students read before class. And there's a lot of great learning management systems out there at this point. This is developed by Eric Mazur. I don't use it, but it looks fantastic from my point of view. And our goal, even once students are doing this, cover less material, but do it well. And what is the point of rushing through all that content when you know students don't get it? You see that on the final exam. You have that evidence in front of you. So why do we do this? When we make this shift to liberate ourselves from the role of the purveyors of information, then we can take a much more meaningful role in the learning process, much more like a coach. Even if it's a large class of 300 students, we can still construct a learning environment that is designed to help them with the challenge of sorting through all these new ideas. And then we can provide our meaningful insight, those little gems that we've built up over the years. But it has much more meaning to them, and it's a much more meaningful process for us. It's a much more rewarding experience as a teacher. And then, who has the time? And to help you folks out with this, I have a modest proposal to share with you. And it all has to do with this. But you have a course on your books, that independent reading course. This is a great opportunity for you to really help out your graduate and your undergraduate students. It's a win-win situation for faculty and students, because you need help and time with making these changes to your teaching. And they need apprenticeship in the science of teaching. So you can use this literature review course to have that student summarize the education research in the course that you're teaching. You can have them watch the classes, interview students on the way in or on the way out, or take a look at those problem sets. What do you notice are the common challenges, difficulties, misunderstandings? Or come up with some lesson ideas. How can we do this different or better? This would be a great opportunity for faculty and those undergrads or graduate students. And the physics education research at this point is so wide and robust, you'll find great material for all your standard undergraduate courses. You'll find stuff on quantum mechanics, on thermodynamics, electrodynamics, all your favorite dynamics. They're all in there. And your literature review students will be exposed to the scholarship of teaching and learning. And you'll have this helpful hand to at least get you moving in that direction. But one of the most important reasons why I think we need to change the way we teach is for the health of the physics community. I think many of us have had this experience where we go to the cocktail party, and inevitably people ask you, so what do you do? Oh, I'm a physics teacher, or I'm a physicist. And you get responses probably kind of like this, but they go along with the bulging eyes, and maybe it's slowly backing away. They're looking at you like this sort of magical and otherworldly creature. Oh, physics. Right? Physics has this reputation, which sometimes we are unfortunately proud of, that physics is hard. And this has a real effect upon the physics community and the kind of people who think they can do physics. So, in order to improve the health of our physics community, well, we can see the results nowadays if we look at the population of women within our community. It's still extremely low. And this should be a very worrying statistic for all of us. Another important reason to rethink is because of, I call it the social contract with teaching. Now, you may not remember signing this particular contract, but it goes something like this. Like, the public expects us to teach their children well. And then in return, we get to do all the crazy science that we want, like make black holes in our hadron colliders and things like that. Now, you may not agree with this, but I strongly believe that contract is there. And we ignore it at our peril. Because there can come a time when misinformed people will make decisions about our life's work and effort and turn it on its head. I think this is really important for us to be conscious of. So, our theme today was build a better student, build a better teacher. And I'll end off by showing you my evidence. With the physics program that I've helped to create and share across Ontario, we've measured the success of our students using the force concept inventory. And these are from my own classes over a number of years. To give you a sense of what these results mean, at my school, the average score when we finish grade 12 physics on the force concept inventory is 81.5%. When this program has been adopted by other teachers, they get similarly high scores. And this is one of the selling points of science, the reproducibility of results. So other teachers who are not physics experts, who have received relatively little training, can take the program and literally become better teachers. Compare this with the average score for students starting physics at Ryerson. 39%. Now I know what you're thinking. But let's compare that with the kids starting at U of T. 57%. And my guess is McMaster is somewhere around there. And for the kids starting first year physics at Harvard, we are on average producing superior students. This is our empirical evidence that we now can help teachers teach better than the best lecturers of the past could have ever thought possible. And for the students themselves, if I give this survey of attitudes to my students, we're getting by and large positive shifts. Their thinking is becoming more expert-like than before. We're reversing the trend that we see in higher education. So our students are clearly better. And most promisingly, we're seeing strong improvements in interest levels, conceptual understanding for our female students. And this is my hope that we can start to change the face of our physics community. Now, when we look at an expert, their abilities seem magical. When you watch that concert pianist perform, or the mathematician do his wizardry, it can seem mystical, otherworldly. But the research shows that the real difference between the novice and the expert is very high-level training. And so, this is my prediction for physics education. I strongly believe that as physics education improves over the next number of decades, that we will be able to train the average adult of average level intelligence to become a well-regarded, expert-level physicist. I don't think these are the ravings of a crazy high school teacher. I think science is on my side. And so I strongly encourage all of you to join this scientific revolution for teaching. I'm hoping it can help to turn a new page within your own teaching careers. And also give you bragging rights so that you can tell perhaps your grandchildren or your great-grandchildren who will take for granted this new way of learning that you were part of the great teaching revolution of the 21st century. Thank you very much.
Thanks, Chris. Are there any questions? Karen? Chris, what was the one negative on your graph? Sense making.
Sense making.
What is that?
That has to do with their approach to physics of, did they try to make sense of the ideas or are they tending to memorize them? And in most of the results that I've seen, that's been the most negative of all of them. And it's a bit mysterious. It's one that we're working on. Yes, sir?
Yeah, so my question has to do with the people who would otherwise have gone on to become experts and get their undergraduate degree, how these sorts of programs impact them. Like you say, you might have to sacrifice the amount of content you cover in order to implement these methods which will improve the quality of education for lower students. But for the students at the top, is this going to be sufficiently challenging for students who are passionate and interested in going on and pursuing a career as an expert? Will this be enough for them?
Yeah, what I find from my own teaching experience is that it's an extremely rewarding process, especially for my most talented students. Because while to us it can seem like they pick up on the ideas really fast, and they have a tremendous aptitude for solving the problems that we present them with, if you say, whoa, 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 slow down, explain to me your idea, your understanding, they have a lot of difficulty with that. Often because they don't have the tools to explain well, but other times because that understanding in fact isn't there, but they are very good with the algorithmic procedures that allow them to solve these problems. So I found it to be very beneficial, and I've broken up my force concept inventory data into quartiles for strong, medium, and weak students. And it's the top students who've gained the most from this learning process. Yes, sir?
we kind of have a model of the sort of learning you're talking about. We go to graduate school. What would you see as the impact on graduate school of introducing the sort of active learner concept 4 years earlier?
I think the biggest impact is if you take a look at a lot of the experiences of the high school student or the undergraduate student, most of them never have the experience of having learned where does scientific knowledge come from. That's kind of the essence of graduate school, where your task is to start generating genuinely new scientific knowledge. But until you get there, you've often never seen that process yourself. And that's such a fundamental part of doing science. How do we generate scientific knowledge? And with this type of learning, that's an intrinsic part of it from the earliest level. So I think the students gain a much deeper appreciation for experimental techniques and a greater understanding of how and why the scientific concepts are useful. They've seen the ideas that go into generating the scientific concepts. And that helps to make so many more connections in their minds so that they know, okay, this is a useful tool for that kind of situation. So I think it's extremely beneficial because often our students don't see that until they get to the graduate level. And then they don't have the skills that we might expect of them to, okay, here's a situation, come up with a good experimental design. How often have they done that in the past? And that can be very challenging for them. Yes, sir?
You often hear the phrase that it takes 10,000 hours of practice to make an expert.
Yes.
I don't know if that's wrong-headed or not, but how do you regard an idea like that in this context that you're
that idea has become very common in popular culture, and it's been unfortunately debased a bit. There's a lot of context that goes into that. It takes 10,000 hours of deliberate practice under expert coaching to reach what is generally considered competent, world-class, expert-level skills. And I think that's very valid, the idea. And it's our job to provide that deliberate, focused practice with as much of that expert coaching as we can. And that helps our students get from the novice to the expert as quickly as possible without the wasted hours in between. Yes?
So you talked about having students do group work or sort of explain things to each other, but are there other things that we can do in our tutorials to help our students kind of be better active learners?
The number one thing to do to help your students is basically to stop talking. That's a really, really good starting point. And after that, it's to start listening. Because when you begin listening to your students' conversations, you start to learn so much about what is going on in their minds. Because, again, as experts within our technical fields, we have relatively little knowledge and understanding of what happens when these novice humans interact with new physics ideas. And it's highly nonlinear, chaotic, all sorts of things go on. And we need a lot of time to study that to become experts at teaching. So the first thing to do is to make sure it's your students who are doing the work and the talking. So if you have them working away in groups on their problems, that's great. And try to structure that as much as possible. So if that's a matter of, instead of taking up a question, the groups have been working on it, and you take up a question on the board, well, maybe you can find a way to have groups share parts of the idea. So there's many, many different ways to do that. But the most important thing is who is doing. Because it's the person who is doing who does the learning.
One of your requirements of active learning was to have your students read the material before class. Have you had difficulty getting students to do that in the past? And how do you overcome those?
At my level, I've actually removed that requirement. For a university where there is such a premium put on content, this is a way that you can have students get that content, that information, so that in class you can do something much more active and engaging. In my classes, I don't want them to pre-read because, again, research supports this idea. If you present students with a pre-packaged concept like momentum, and then you ask them to, okay, now let's think about momentum. Well, they don't, because it was given to them by an expert. So whatever the equation is, it's correct, and it will give them the answers that they need when you give them the test question. So what's there to think about? But if you reverse that process, you say, okay, look at the ideas involved with momentum, the concepts behind it, and let's piece together the formal idea of momentum. Then you get them doing a lot of very genuine, nuanced thinking, and then they appreciate the process of generating scientific knowledge. So it's not the approach that I use. I prefer them to come in without that reading. But we take more time. And I have the liberty to decide because there's nobody from the ministry looking over my shoulder. And I say, well, we're just not going to get to that unit. We're going to do this really, really well.
This is risky on my part. I'll explain in a moment. I'm currently teaching 2 courses. I'm elderly and Luddite, so I didn't think about active learning. But listening to you, one of them is actually active learning. It starts after a brief introduction with experiments, people work together in a team, they then report back to the whole class on what they've discovered. Sounds pretty inactive to me, probably. I'm teaching another class which is just the poor people listening to me. Okay? As far as I can tell, the performance of the same students mostly is very similar. I mean, shockingly, on a class test just recently, just over 2/3 of the students got, on the traditional way, me yakking, got over 90%. So that's wrong. I'm obviously doing something wrong there. And the reason it's risky is at least one of the people who's suffering through both courses is actually sitting here. Probably now. But, so, I mean,
yeah,
what's going on?
One of the challenges is, especially when we look at our experience as teachers and experience being students in the past, our sample size for our data set is very small. And there are necessarily large statistical variations in the results that we get. And the other is there's